benzene reactions,
Yeah.
and
Uh-huh.
then you have to like reduce them. So you have to like remove the
Uh-huh.
EDG or the EWG. That's something I personally found myself struggling with, but we can get to that at a later point.
Oh, right. Like after the electrophilic aromatic substitution reactions, you learn about the helper reactions, right, for synthesis.
Yeah.
Yeah, yeah, we could talk about that.
Yeah, and then like
Okay.
another thing I was like super confused on was like um I think Helix covered it not last class but like the class before today. He would have like
Mm-hmm.
it was like met synthesis when you're using EDGs and EWGs. So like you have to
Mm-hmm.
choose which group comes in first on the benzene
Mm-hmm.
ring.
Mm-hmm.
Those
Right,
were
right,
like
right,
the
right.
yeah,
Yeah,
like
like
those were
for
like the two topics that's super confusing for me.
okay, okay, yeah, let's do that. So let me go over just what electrophilic aromatic substitution is in general, talk about the reactions, reagents, and then start talking about also para-directing, meta-directing, activators, deactivators, and then do synthesis problems based on that. Okay, so electrophilic aromatic substitution, abbreviated as EAS, is a mechanism that has five reactions that you'll be learning about, but the general mechanism will have three steps. The first step is to generate the electrophile. The second step is going to be to have the nucleophilic benzene attack the electrophile that we created in the first step, which will break aromaticity, right? We could also talk about that, but that would make it less stable if we break aromaticity, right? And then the third step here is that we are going to restore aromaticity, right? By doing an elimination reaction, like an E1 type reaction, right? So that's going to be the same general steps for EAS mechanism. And there's five specific types of EAS reactions that you need to know. The first one is going to be aromatic halogenation. The second reaction is going to be aromatic nitration. The third reaction is going to be aromatic sulfonation. And this reaction here is reversible. We could do desulfonation, and this will be important later on for synthetic strategies because this reaction tends to block the para position for synthesis, right? And then we could say desulfonation here to go backwards, right? And then we have the next two reactions, which are going to be the Friedel-Crafts reactions, the reactions that will add carbon-carbon bonds, right? The first one we're going to talk about is Friedel-Crafts alkylation. And then the other type of Friedel-Crafts reaction is Friedel-Crafts acylation. Okay. So now let's talk about the first reaction, aromatic halogenation. I'm going to give you the general reaction and then the mechanism after that, right? So the benzene here, well, before we go over that, let's go over the mechanism step by step generically, right? General EAS mechanism. Because a lot, like all of these reactions here, right? Halogenation, nitration, sulfonation, desulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation, we follow the exact same three steps here, right? The steps 2 and 3 will be the exact same. The difference between all five reactions is going to be the first step, how we get to our strong electrophile, right? So the general EAS mechanism will look like this, right? Right? Benzene here will be our nucleophile, right? Where any carbon of this benzene here can be the nucleophile. because there are pi bonds all around these carbons. And when you draw the resonance structure like that, we see that one of the carbons can have a pair of electrons, right? Which can act as a nucleophile and attack an electrophile, right? So let's say an electrophile was already formed, right, after the first step, and we use this starred carbon here as the nucleophile. That nucleophilic carbon right there is going to attack the electrophile and give us this intermediate right here, where we used this bond right here to create this neo bond between the starred nucleophilic carbon and electrophile right there. But because this carbon here lost a bond, that carbon will be a carbocation now, right? So that's going to be the second step. Nucleophilic benzene ring attacks the electrophile that we created from the first step, which breaks aromaticity, right? Before this benzene was aromatic, happy, and stable, right? But now it's gonna be sad, angry, less stable, right? Non-aromatic, right? Because it is not fully conjugated. There is an sp3 roadblock there. Now the third step here is to restore the aromaticity by doing elimination. So you're gonna use some sort of base, and the base here will be different depending on what reaction you use, right? Draw out the hydrogen here explicitly and do an acid-base reaction. And then the bond between this proton and carbon being grabbed will go onto that bond to create a double bond right there, restoring aromaticity. E1 mechanism here, right? Which will give us this product right here. Okay. Now that would have your base have a proton, and if your base was negatively charged, right, then now it would be neutral. If your base was neutral, then it would be positively charged, right, because it gained a bond right there. Okay. Any questions on this general mechanism before we move on to the very specific reaction, aromatic halogenation?
Yeah, I had like a question. So
Yeah.
I noticed like in some practice questions they would use like zinc, like it would be like zinc, and then it would be in brackets, I believe mercury, and then it would also be like HCl.
Yeah, so that is a helper reaction that will not be part of these 5 reactions right here. That's going to be a chapter 16 reaction that will help you do synthesis, where you could convert an orthopara-director into a meta-director, or meta-director to orthopara-director, which we could talk about after we talk about
Oh,
these
I
reactions.
see. I thought it was like
Right.
another type of aromatic
Uh-huh.
halogenation.
Yeah, no, that zinc, and then Hg, like mercury HCl, is not EAS reaction. It doesn't affect
Okay.
the benzene ring, right?
Okay.
Right. Okay. So now let's talk about halogenation here. Aromatic halogenation. So for aromatic halogenation, I'm going to give you the general reaction, predict the product, and then move on to the mechanism. So we will have that benzene right there with no groups attached to it. So any carbon could be the nucleophile here. We can have Br2 and then Lewis acid catalyst, FeBr3, right? It could have also been AlBr3, right? But what that would do is that would substitute one of the protons into the bromine, right? Like one of the hydrogens of the benzene would be substituted with the bromine, right? Like that, right? Okay. Now here's the mechanism. Right? The first step is to generate the electrophile, right? So to generate the electrophile, I'm going to draw out our reagents like this specifically. This is our Br2. Our Lewis acid catalyst is FeBr3. And think of iron and aluminum and boron as those atoms that would be neutral with 3 bonds, right? Because we know BH3 has 3 bonds. It's missing an octet, right? It's missing 2 electrons, but it's neutral, right? So because it's missing an octet, we have an empty p orbital, right? Which would be the electrophile. It's willing to gain electrons. So this iron here has 3 bonds to bromine, right? Meaning that it is having an empty p orbital. It's missing 2 electrons. So one of the bromines here, the Br2, we use one of its pairs of electrons to attack that iron right there to create a bond between that bromine and iron to give us this intermediate right here. Right, okay. Now, once you have this species right here, think of this as a good leaving group. Okay, and think of this as your electrophile. Right. Now, I'm going to do it the way that Helix taught it. So specifically, let me look at how he did halogenation, right? Because the benzene could like attack this electrophile, kick out the good leaving group right away, or the leaving group could just leave by itself, creating a bromine plus ion, and then this will leave. But let me see how Helix does it so we can do it his way here. So we'll look at aromatic halogenation. Okay, so he does it this way. Okay, so now that's our first step. Our second step is going to have the nucleophilic benzene attack the electrophile that we formed in the first step here. Right. So that is going to be the carbon that's nucleophilic, attack that electrophilic bromine, and then kick out that good leaving group right there, which will give us aromatic intermediate right here, right? Where we have a new bond between the carbon and bromine right there. And we broke the aromaticity because there is an sp3 lock here. There's no full conjugation here now, right? Now, this is the leaving group that left. The iron is still negatively charged because it has 4 bonds, but this positively charged bromine is now neutral because it gained a pair of electrons from this bond right here, right? Now, the third step is to restore the aromaticity by doing an elimination reaction, which we could use this as the base for this specific reaction. Right? Iron is negatively charged, so it wants to like become neutral again. So bromine here will use this bond to grab that proton and give us our aromatic ring back here. Okay, nice. And that is our mechanism where we have HBr as a byproduct from this acid-base reaction. And we have our Lewis acid catalyst, right? FeBr3 reformed in the mechanism here. Okay. Any questions on this reaction and mechanism?
Oh yeah, I just wanted to double check.
Yeah.
Is there any like stereochem that we have to be worried about?
No sterica that we need to be worried about here in this mechanism.
Okay.
Good. Nice. Okay. And that was the third step of the general mechanism, restore aromaticity. When you do the mechanism, you don't have to number it like this. It's just to help you like know what's going on, like big picture, right? First step, create the good electrophile. Second step, nucleophilic benzene attacks electrophile, breaking the aromaticity. And then the third final step, restore aromaticity with the base, right? So instead of like memorizing like step by step, you could understand it like this, or you could write the entire mechanism in your note card and you could follow that as well. Okay, nice. The next reaction we're going to talk about is aromatic sulfonation here, or no, nitration, aromatic nitration here. Okay, so for aromatic nitration, here's the general reaction. We'll have this benzene right here, react it with these reagents, specifically HNO3, H2SO4, And what this would do is that this would substitute one of the hydrogens with an NO2, a nitrate group, right? Like that. Okay. Now here's the mechanism, right? So the benzene here will be the nucleophile. Well, no, the first step is to generate our strong electrophile, right? So I'm gonna draw out the HNO3 out like this. So our HNO3 from the reagents is gonna be this in Lewis structure. The nitrogen will be right here, double bonded to an oxygen, double bonded to an hydroxy group, single bonded to a negatively charged oxygen, and the nitrogen itself with 4 bonds will be positively charged. So this overall structure is neutral because positive and negative charges cancel out, right? We have 1 positive charge and 1 negative charge, so that cancels out to a net charge of 0, neutral, which is represented in this condensed formula here, HNO3. We see 0 formal charge here, right? But nitrogen itself has a full formal charge of positive 1, and oxygen here has a full formal charge of negative 1. Okay. Now, we have acidic conditions here with sulfuric acid, right? So we're gonna protonate this hydroxy group. I'm gonna draw out the sulfuric acid out in this form, where this hydroxy group is gonna grab a proton from the sulfuric acid and give us this intermediate right here, where we form an oxonium ion, which is a good leaving group, right? Now, we could drive that good leaving group to go off by having this negatively charged oxygen atom with this 3 pairs of electrons, right? One of the pairs of electrons would go here, create a double bond between the nitrogen and oxygen, and to conserve the octet rule here, right, to prevent nitrogen from having 5 bonds, we're gonna kick off the good leaving group at the same time that we formed, which will give us water as a byproduct, right? This is the water here that left. That's now neutral. And this NO2 electrophile that we want in the mechanism, where the electrophile here is this positively charged nitrogen atom right here. Okay, now that's done with the first step. Let's bring that over to our second step, where the nucleophilic benzene ring attacks our electrophilic molecule that we created in the first step. Let's say this is the star nucleophilic carbon. This is the dot electrophilic atom, the nitrogen atom. Attack that. We're making a new bond between the star and dot, between a nucleophile and electrophile. To conserve the octet rule, we're gonna pop one of the double bonds onto the oxygen and give us this intermediate right here. Right, where we broke the aromaticity, but now we have our NO2 that we drew out in the general reaction. This NO2 right here is this exact NO2 right here expanded out in Lewis structure, right? Now, the third step here is to restore aromaticity using a base, and our base here is the conjugate base of sulfuric acid, which is gonna be that. So we're gonna do elimination by those 2 arrows, reforming our aromaticity here. Like that, right? And you don't have to draw out it like this in the predicted product. You could have also drawn it like this as well to make it more clean, like that. But know that this NO2 here looks like this when it is expanded out. Okay. Any questions on the nitration reaction and mechanism? Okay. Now let's move on to aromatic sulfonation and desulfonation here. Right. Okay. And this reaction here is reversible. Aromatic sulfonation, desulfonation. Okay. So let's say you have a benzene, and on the arrow you have SO3, H2SO4. What that is going to do to the benzene is substitute one of the hydrogens with an SO3H group. Right. Now, if you want to desulfonate the benzene, get rid of the SO3H group, get back your proton, you could use dilute hydrosulfuric acid, H2SO4, water, and heat. Let me double check that on the notes here real quick. Sulfonation. Yep, so it's just dilute sulfuric acid and water. No heat needed. Okay? Okay. So here's the mechanism for sulfonation. Okay. So the first step is to generate our electrophile, which is gonna be here, right? We have SO3, which is represented like this, and we have a strong acid, sulfuric acid. So we're gonna protonate one of the carbonyl oxygens, oh no, one of the double bonded oxygens here, right? With two pairs of electrons. One of the pairs of electrons will grab a proton, kick out the conjugate base of sulfuric acid, and give us this right here. Okay. Okay. Now we have our strong electrophile, which is going to be this sulfur here, right? Think of this as the good leaving group, right? Because when a nucleophile comes in to attack this electrophilic sulfur, we could pop the double bond onto the oxygen like that, right? This positively charged oxygen here is angry, unstable, because that's a full positive charge right there, right? Now that's done with the first step. Now our second step is to have our nucleophilic benzene attack our electrophile that we formed in the first step, pop the double bond onto the oxygen, and give us this intermediate here where we break the aromaticity. Right? And this right here is our SO3H that we drew out in the general reaction here. Right? Expanded out, it would look like this right here. Okay? Now, we broke the aromaticity here. So the third and final step, we'll have the base, which is the conjugate base of sulfuric acid that we used in the first step to do elimination and restore aromaticity. And I'm gonna condense this SO3H structure down into this condensed structure here. Okay, now that's the mechanism for sulfonation. The mechanism for desulfonation, where we go backwards here, right, is gonna be the exact same thing as this, but going backwards, right? So we see that if we start off with the sulfonated benzene here, where we go backwards, our first step would have this non-aromatic structure with the SO3H, and going backwards after that, we have the benzene and this positively charged SO3H, and then we could go backwards a bit more to have the neutral SO3, right? So let's look at that here. The mechanism for desulfonation here is going to look like this. So I'm gonna draw out the sulfonated benzene in its expanded structure like this. And we are in acidic conditions here, so I'm gonna draw an acid right here. And I know that because we're going backwards, I know that the next step is gonna have this structure. Right here. So we got to ask ourselves, how can we convert this structure into this structure given acidic conditions, right? we see that this carbon here has a proton, whereas this carbon here does not have a proton. So to give this carbon a proton here, we could use the acid that we have in acidic conditions. So this carbon here is going to be the base that will be protonated by the sulfuric acid, which will give us this intermediate that we want if we are going backwards, right? That pink proton that I highlighted is this pink proton right here. And because this carbon here lost the bond, it is now a carbocation, and we now have our non-aromatic intermediate structure here, right? Okay. Now we know before that, right, we had the neutral benzene ring and this electrophile right here. Right? Because we know that this carbon here attacked the sulfur, popping the double bond onto the oxygen to get into here. But we want to go backwards now. And to go backwards here, we have our aromatic structure back. The SO3H is now gone. But we do not want to have the conjugate base of sulfuric acid to grab the proton and do the elimination reaction to reform the benzene, because that will go back to what we started with. The SO3H group is still there. Okay, but we want that to be gone. So to do that here, we are going to, let's see here. Okay, can go like that. SO3H. Okay. So we see that there is a double bond here between oxygen and sulfur, which was not there before. And to create that double bond right there, we see that this oxygen has 2 pairs of electrons, whereas this oxygen here has 1 pair of electrons. We could use one of the oxygen's pairs of electrons to go make a double bond between oxygen and sulfur like that, which will give us this right here. And we'll break this bond and create a double bond right there, which will give us this aromatic benzene back, right? This pink proton here is still there, right? And this is going to be the desulfonation mechanism where we have our neutral benzene structure back like that. Okay. Any questions on sulfonation and desulfonation before we move on to the Friedel-Crafts reactions? Okay. Okay. Now let's go over the Friedel-Crafts reactions. Now, before we talk about Friedel-Crafts reactions, let's give a review on what it is. Friedel-Crafts will make carbon-carbon bonds, right? And there are going to be 2 that we're going to be talking about. We're going to be talking about alkylation and acylation, right? Alkylation will have 3 synthetic limitations, whereas acylation will only have 1 synthetic limitation. And that 1 synthetic limitation that the acylation has, the alkylation also has, right? Which is going to be that Friedel-Crafts reactions do not work on moderately strongly deactivated rings. And we'll talk about what that means. Deactivated rings. Okay, so let's first talk about alkylation, right, which is a tricky one. Like, out of all of the electrophilic aromatic substitution reactions, Friedel-Crafts alkylation is going to be the most involved, right? The most difficult, in my opinion, because there are a lot of scenarios that could go with this. Okay, but let me just give you simple scenario here. Let's say I have a neutral benzene and I have this haloalkane with a metal Lewis acid catalyst, AlCl3. Now, to predict the product quickly here, this is going to be the nucleophile, this is the electrophile, and think of this halogen as the good leaving group. we can make a new bond between the star and dot, right? That's the new bond right there. The dot is attached to two methyl groups, 1, 2, like that. The good living chlorine gets kicked off. Now, not all Friedel-Crafts alkylations would be this easy to predict the product because there is a carbocation intermediate in this mechanism that would be formed, right? And because of that carbocation intermediate, it is going to be tricky to predict the product quickly, right? But let me show you the mechanism of this and then show you those different scenarios. Okay, so let's look at this mechanism here. Okay, so let's say I have this benzene. Well, the first step of all EAS mechanism is to generate the strong electrophile. So this is our haloalkane. This is our metal Lewis acid catalyst. This chlorine here has 3 pairs of electrons. This aluminum here has 3 bonds, empty p orbital. So the chlorine is going to attack the aluminum and give us this intermediate right here. Right, where we see that this right here is a good leaving group, right? And now think of this as SN1E1 type mechanism. If it's able to form a secondary or tertiary carbocation, then it's just going to leave by itself first because that is a stable carbocation that could exist on its own. So this good leaving group is just going to leave to form a secondary carbocation here. Now, whenever you form a carbocation intermediate, you have to stop and look for any rearrangements that you could do, like a hydrogen shift or an alkyl shift. Right, to make the more stable carbocation. Okay, in this case right here, we have a secondary carbocation because this carbon here with the positive charge is attached to 2 other carbons. If you look to the right of it, that's a primary carbocation. If you look to the left of it, that's also a primary carbocation. So it's already at its most stable position. So we do not have to do any rearrangements here. Right, so we're done with the first step here. We generated our strong electrophile, where our second step of the mechanism here now is to have the nucleophilic benzene attack the electrophile that we formed in the first step, start the nucleophile, dotted the electrophile, and give us this intermediate here, where we break the aromaticity, make a new bond between the star and dot, new bond between the nucleophile and electrophile, positive charge on that carbon right there, and then this carbon right here will be attached to 2 methyl groups like this. And now the third step here is to restore the aromaticity, right? So the base that we're going to use here is going to be the good leaving group that left earlier, the AlCl4, where the chlorine is going to grab that proton, E1 type mechanism to restore that aromatic benzene structure. HCl is a byproduct, and our metal Lewis acid catalyst, AlCl3, gets reformed in the mechanism here. And we see that this Friedel-Crafts reaction made a new bond between carbon and carbon atoms, right? All Friedel-Crafts reactions will make a new carbon-carbon bond. Okay. Any questions about this scenario of Friedel-Crafts alkylation? Okay. Okay. So now it can get trickier, right? Because we have carbocation rearrangements. There's 3 scenarios for that. We already talked about the first scenario, right? Where like one of the first scenarios, no carbocation shift is needed, right? No carbocation shift is needed here. But another scenario where no carbocation shift is needed would be this right here. right? Where if we have that benzene right there and we have this alkyl halide or haloalkane with AlCO3, to predict a product quickly here, right? Get rid of the bond attached to the good leaving group and the leaving group and have a carbocation right there, right? We know that this is unstable because this is a primary carbocation, it cannot be formed, and next to it, adjacent to it, is also primary carbocation, so it cannot be formed. So there's no like rearrangements here. So that means SN2 reactions can happen, which I want to show you the mechanism here right now. Right. So this is the other category actually. Right. The other category would be an SN2 type mechanism, right? Not SN1. Okay. So just to predict the product quickly here, this is going to be the product where this is the star, this is the dot, this is the star, this is the dot, this is the near bond between the star and dot, right? And the dot no longer has the chlorine, but it has the methyl. So here's the mechanism for this specific Friedel-Crafts alkylation reaction, right? The first step of this EAS mechanism, generate our strong electrophile. So this is our haloalkane, this is our metal Lewis acid catalyst, AlCO3. The chlorine will attack the aluminum and give us this intermediate here, where aluminum with 4 bonds will be negatively charged, chlorine with 2 bonds will be positively charged. We have our good leaving group, which is this. Think of this as bromine or chlorine. Now, previously, this good leaving group just left by itself, right? Forming the carbocation. But in this mechanism here, we cannot do that because when we do that, we're going to form a primary carbocation, which is unstable. It cannot exist, right? So what we will do instead is that we will say that this is the electrophile, this is the good leaving group, and we move on to the second step where the nucleophilic benzene does a backside attack and kicks out the good leaving group. So this would be an SN2 mechanism here instead of an SN1 E1 type mechanism, right? So this nucleophilic carbon here will attack this electrophilic carbon, kick out the good leaving group, and give us this intermediate here where we broke the aromaticity here. Where this is the starred carbon, this is the dot carbon, this is the new bond between the star and dot carbon, and then this carbon right here that lost the bond will be positively charged, right? And to restore the aromaticity, we could use the base that we just kicked out to do an elimination reaction and restore aromaticity. Forming HCl as a byproduct and the metal Lewis acid catalyst AlCO3 again, right? Any questions on this specific type of Friedel-Crafts alkylation reaction before I move on to the next type?
I have a question.
Yeah.
What is the meaning of the word like alkylation and acylation so we like don't get confused between the two?
Yeah, so that's a good question. Very similar words, right? Both starts with A, both ends in ation, right? Alkylation, acylation. Alkylation will add an alkyl group to the benzene, which is a hydrocarbon chain, right? Carbons and hydrogens, alkyl group. Acylation, when you see the word acyl, right? Acyl, think of that as carbonyl. And do you know what a carbonyl is? Does that sound familiar? That term, carbonyl? Carbon, double bonded to oxygen, right? So when you see a carbon double bond to oxygen, that's a carbonyl or an acyl group. And there's 2 carbonyls that you will learn at the end of this quarter, 118B. You're going to learn about aldehydes and ketones, right? Which are chapter 17 and 18, right? Aldehydes look like this. Ketones look like this, right? Both have carbonyls or acyl groups, carbon of 1 oxygens. Aldehyde has 1 hydrocarbon and 1 hydrogen, right, flanking the carbonyl, whereas a ketone has 2 hydrocarbons. It could be the same or different, flanking the carbonyl. Now that's going to be chapter 17 and 18, the last chapters of Chem 118B. So when you see acylation, know that you're adding a carbonyl to the benzene. So acylation will add something like this to the benzene. And the R group here could be different depending on what reagent you have. But acylation will add an acyl group or carbonyl group to the benzene like that. Whereas alkylation will just add an R group, a hydrocarbon chain like this. Like whatever the hydrocarbon is. It could be methyl group, ethyl group, isopropyl, tert-butyl, sec-butyl, cyclopentyl, cyclohexyl group. Any random alkyl hydrocarbon chain like that. Any questions on that? The difference between alkylation and acylation, so you don't get difference between the wording for the reaction here?
No, I think that makes sense. It was a really good explanation.
That's good. That's good. Okay. So let's move on to the next scenario of alkylation. The next scenario is going to be something like this. When we have this benzene right here, and we react it with this alkyl halide with AlCO3, if you went straight for predicted product quickly without doing the whole mechanism, and you try doing it like this, where this is the nucleophilic carbon and this is the electrophilic carbon, and you try to make a new bond between those, get rid of the chlorine to get this right here. New bond, star dot. Get rid of the chlorine, it left. The dot has an isopropyl group and a methyl group, right? This would be the incorrect product. That would not be your product, right? And that's because we know that there is a carbocation intermediate. So let's say the leaving group left, forming a carbocation at that position. That is a secondary carbocation. And we see here to the right of it, there's a tertiary position, a more substituted position that it could be more stable in. So we're going to do a hydride shift here to form the tertiary carbocation, which this here would then be our electrophile. So let's stick with the same problem, but without doing the mechanism. How to pick the product quickly without doing the mechanism, but correctly this time. Right, so I'm going to put in quotation marks here. Imagine the good leaving group leaves, forming a carbocation on where the carbon held the good leaving group. In your head, do a rearrangement step to form the more stable carbocation intermediate, where we know now this is the starred carbon, this is the dot carbon. And if you use that method, you will end up with the right product, where this is the starred carbon, this is the dot carbon, this is the new bond between the star and dot. The dot is attached to an ethyl group and two methyl groups like that, right? Ethyl group here, right? Two methyl groups are here. Okay, so this structure here is different than this structure here, and that's because of carbocation rearrangement right there. Okay, now let me just quickly do the mechanism. Stop me if you have any questions, right? The first step of this mechanism is going to generate a strong electrophile. So we have our alkyl halide, our metal Lewis acid catalyst AlCO3. Chlorine attacks the aluminum with the empty p orbital, form this intermediate with a good leaving group, where aluminum with 4 bonds would be negatively charged, chlorine with 2 bonds would be positively charged. This species here is our good leaving group. We kick out the good leaving group, form our carbocation on that spot that lost their bond. And whenever we form a carbocation, we know that we gotta stop and wait for any rearrangements that could happen, which there can be here, to form a more stable substituted carbocation here, which this is gonna be our electrophile, and that's done. We have our electrophile here after the first step. Now we're bringing in our second step, the nucleophilic benzene. Attack the carbocation, break the aromaticity of the benzene to make a new bond between a nucleophilic and electrophilic carbon. Attach the decorations. The dot carbon, the electrophilic carbon, has an ethyl group. Draw the ethyl group out. And it has two methyl groups like that. Right. This carbon here lost the bond, so it's positively charged. Now the third step is to restore aromaticity here. So we could use this base to do elimination and restore our aromatic benzene ring here. Right, where our byproducts would be HCl and metal Lewis acid catalyst AlCl3, like that. Okay. Okay. Now there is one more scenario that I want you to know, right? Which is the tricky scenario here. This is gonna have concerted shifts. Right. So let's say I have this benzene and I have this alkyl halide right here. We know that this is the primary position, so when the leaving group leaves, we'll have a primary carbocation, right, which cannot be formed in the mechanism, but there is a tertiary position nearby. We can do a concerted shift to have the carbocation at that position instead, right? And this is in quotation marks. Just imagine that the leaving group leaves. There is a carbocation right there, which would not be formed in the mechanism. This would not be formed in the mechanism. This is just what you could use in your mind to predict the product quickly here, right? We see that we could do a hydrate shift to form the more stable substituted carbocation, which is this tertiary position right here. And just to predict the product quickly here, connect the nucleophile and electrophile to get our product like that. But this right here does not get formed in the mechanism. But just think about that in your mind to predict the product quickly in the mechanism. Okay, now this star will be bonded to this dot. The dot has 3 methyl groups coming out, 1, 2, 3. So we draw 3 methyl groups coming out, 1, 2, 3, which is a tert-butyl group like that. Now here is the actual mechanism for this, which will involve the concerted shift. Okay, so we will have this benzene. Oh no, the first step is to generate the good electrophile. So we will have this alkyl halide, this metal Lewis acid catalyst AlCO3, the chlorine attacks that aluminum, form this intermediate, have our good leaving group. Now from here, we cannot kick out the good leaving group by itself, like we said, because that would form a primary carbocation. We do not want that. But if you look right next to it, there is a more stable tertiary position, which, like, if it was secondary, you could do the same, right? You could do a hydrate shift and then kick out the good leaving group at the same time, simultaneously, which is the concerted shift right there, which will give you the more stable, more substituted carbocation right away, like that. Right? Which this is our electrophile that we could use for the benzene to attack in the second step. Make a new bond between the nucleophile and electrophile. Positive charge on the carbon that lost the bond. This electrophilic dot carbon here has 3 methyl groups, so we draw that 3 methyl groups coming out like this, 1, 2, 3. And now the third step here is to restore aromaticity by using this base that we formed earlier, right? Chlorine, grab that proton, make a double bond right there. Elimination reaction, E1 type, to restore aromaticity. Byproducts would be hydrochloric acid, HCl, and we reform our metal acid catalyst, AlCO3, like that. Okay. Any questions on this scenario of Friedel-Crafts alkylation? Okay. That's good. Okay. So now we're gonna talk about conceptual stuff about physical alkylation now. We already talked about one limitation here. This reaction will not work on deactivated rings, like moderately to strongly deactivated rings, and we'll talk about that after. But the other limitation, wait, actually no, we have to talk about this now to talk about the limitations. Yeah, I'll talk about the conceptual stuff after I talk about the reactions. Yeah, so let's move on to Friedel-Krauss acylation. Friedel-Krauss acylation. Friedel-Krauss acylation. Okay. So here is the generic reaction here. When we have this benzene right here, and we react it with an acyl group. Wait, this would be two steps. Something like this. AlCl3. Second step, acid workup. This is how you predict the product quickly all the time. Your nucleophilic carbon here will be attached to the carbonyl carbon or acyl carbon, right? The chlorine will no longer be there. So here is the product. Nucleophilic carbon attached to electrophilic carbon. And then electrophilic carbon is attached to a carbonyl, which is going to be attached to an isopropyl group like that. Now, that's the final product. Here's the mechanism, right? There's no carbocation intermediate formed here, so we do not have to worry about any rearrangements. We do not have to worry about hydrogen shifts or alkyl shift, right? Now, first step, generate our electrophile. So we have our acyl group here. We have our metal Lewis acid catalyst here. Chlorine will attack the aluminum, create this species with a good leaving group. Aluminum will have negative charge, chlorine will have positive charge. Now we have our good leaving group right here. We can kick out that good leaving group directly and give us the specific ion, right? Which you might have to know on the test, right? Because this could be a conceptual question. This is going to be an acylium ion. Acylium ion. Right? Because we have an acyl here, and an ion represents a charge. We have a charge on the acyl group. Acylium ion. Now, this isn't the major resonance structure because this carbon here is missing an octet row. It only has 2, 4, 6 electrons. So it doesn't have full 8 electrons. We can draw the major resonance structure here by having the oxygen use one of its pairs of electrons to go down, create a triple bond right there between that carbon and oxygen, which will neutralize the carbon, right? And give it an extra bond and make it have 8 electrons, 2, 4, 6, 8. And now this right here would actually be the major resonance structure, right? It looks kind of weird because we have a positive charge on an electronegative atom here. So it looks weird why this is the major resonance structure. But when you think about the factors that determine the major resonance structure, the most important factor here is that every single atom has to fulfill the octet role. And that overpowers every other factor, right? Every single atom here has the octet role. This oxygen has 8 electrons, 2, 4, 6, 8. This carbon has 8 electrons, 2, 4, 6, 8. But this resonance structure here, not every single atom has 8 electrons. This carbon here is missing 2 electrons. It only has 6 electrons. Like that. But the electrophile here is going to be these acylium carbons here, this carbonyl carbons here, right? Okay. Now that it, like both of these are acylium ions. They're the same structure. They're just resonance structures of each other. But this is the major resonance structure. This is the minor resonance structure. You could use either or for the mechanism. Okay. Now let's move on to the second step where we bring in our nucleophilic benzene ring. And then we bring in our major resonance structure of the acylium ion. You could have used the minor one as well. We know that this is the electrophile, this is the nucleophile. attack to conserve the octet row, pop one of the bonds onto the oxygen, give us this intermediate right here. Right? Where there is no longer a triple bond between the carbon and oxygen, there's a double bond now, where this oxygen is now neutral, and we have an isopropyl attached to the dot. This carbon here lost the bond, so it's now positively charged. Now to restore our aromatic ring here, we could use our base, which was this species here that we kicked out earlier. Chlorine grabs a proton, do elimination, reform the double bond, reform the aromaticity to get our final products here. Form HCl as a byproduct and AlCO3 as our reformed metal Lewis acid catalyst. Now, this right here will be the final product, right, for predicted product. But for mechanism, right, we don't stop here because oxygen here on the acyl group or carbonyl group has 2 pairs of electrons, and we reformed our Lewis metal acid catalyst here, which still has an empty p orbital. So the oxygen here can attack that aluminum to give us this species right here. This is for mechanism here. If you were asked to draw the mechanism, include this step for full credit. Right? Now, because that oxygen here is now having 3 bonds, right? Aluminum AlCO3, negative charge, and aluminum has 4 bonds. Oxygen would be positively charged, and aluminum would be positively charged, right? Negatively charged, I mean. Now, that's the end of the first step, right? To clean this up, we bring in our second step, which is the acid workup, right? H3O plus, we'll clean it up, neutralize the carbonyl or acyl group, and then the AlCO3 will dissolve into ions, right? Al3 plus ions and Cl minus ions, right? Like that, because it is in aqueous acidic conditions here. And this is our final product here, right? Which is the same exact thing as this, but if you were asked to draw the mechanism, include this step as well. Okay. Any questions on this right here? Okay.
Could you just like quickly like talk over what happened after the what was it? The Alexonium ion? I got kind of lost.
Oh yeah, after the acylium ion right here?
Yes, sorry.
Yeah. So do you know how we formed the acylium ion here and the just between these 2 resonance structures?
I think it was like the oxygen would donate its lone pair.
Yeah, oxygen would donate its lone pair to create a triple bond between this positively charged carbon and oxygen, which is why we have a triple bond right here. Like if you were to highlight this lone pair of oxygen right there in green, that would be this bond right there, right? And these would be the electrophilic carbons right here. So now when we bring it down to the second step, where the nucleophilic benzene attacks, this is our nucleophilic carbon, this is our electrophilic carbon, right? Nucleophile, electrophile. The nucleophile here will use this bond to attack the electrophile to form this new bond between the star and dot right there. So we're making a new bond between the star and dot, but if we don't do anything else, this carbon right here will have 1, 2, 3, 4, 5 bonds. To conserve the octet row, we have to push one of the bonds onto the oxygen, right? Because we know that this oxygen here, like, already has 1 bond, 1 pair of electrons and positive charge. Let's say we highlight this in purple. The 2 electrons over there are these 2 electrons right here, which is why this oxygen is now neutral. And then from here, we broke the aromaticity because this carbon here lost the bond, which is why it has a positive charge. And now we restore the aromaticity by using the base right here, which is this aluminum with 4 bonds to chlorine. Because aluminum is negatively charged, one of the chlorines will want to leave with the bond to make aluminum neutral again. So this chlorine here will leave with the bond to grab that hydrogen right there. This bond here holding that hydrogen and carbon will break off and will form a double bond right there, recreating our aromatic benzene structure. And then we reformed our neutral AlCO3, but we don't stop here because the oxygen has two pairs of electrons that can use to attack this aluminum with an empty p orbital, which will create this bond right here and these ions here, which we could clean it up by bringing in a second step of acid to clean up the reaction there. Right.
Thank you so much. I feel like this
Which part
one
of the
is like
mechanism?
the
Yep.
oh, sorry. I feel like this
Yeah.
one is one of the most complicated mechanisms in my opinion.
Yeah. The acetylation one mechanism.
Yeah,
Yeah,
yeah.
it is because there's no carbocation intermediate, but this mechanism here is like going straight through one way for all acetylation reaction. You won't have different scenarios like the different like the previous reaction, the Frikas alkylation, right? That one has different scenarios that will change up the mechanism, but the Frikas acetylation mechanism will always be the same for all acetylation reactions, but it is a little bit more complicated.
Okay. Thank
Right?
you.
Yep, of course, of course. Okay. Now let's take a mini break. We'll go back at 5:10 and then we'll talk about EDGs, EWGs, activators, deactivators, orthopara-directors, the meta-directors, and then the helper reactions for synthesis, like what you talked about before, Ashna, with the zinc and HCl, right? And then
Sounds
do
good.
synthesis problem. Okay,
Sounds
let's
good.
do that. Yeah, I will be back at 5:10. Okay, I'm back. Let's now talk about EDGs and EWGs. So EDG stands for electron donating group, and EWG stands for electron withdrawing group. Right? So if we think about the EAS mechanism here, was benzene the nucleophile or electrophile for um the mechanism?
Nucleophile.
Yep. It was the nucleophile. So what do you think will make the benzene a stronger nucleophile? EDG or EWG?
EDG.
Yep. It would be an EDG because an EDG will donate electrons into the benzene, giving it more negative charge, so it will make it a more nucleophilic, more negatively charged, right? So an AKA for an EDG is going to be an activator. An AKA for an EWG would be deactivator. Because if you have a group withdrawing electrons from the benzene, making the benzene less nucleophilic, it's going to be deactivated in the mechanism. Deactivator. And there are different strengths of EDGs and EWGs. So let's take a look at ortho meta para positions, right? So let's say we have this benzene here and we have a random reference group right here. The ortho position is going to be the first carbon away from it. The meta position is going to be the second carbons away from it. And the para position is going to be the carbon parallel to it or directly across from it. Okay. Now that is just going to be positional terms in relation to a reference group, right? If the reference group is up here, these are going to be the ortho positions. These are going to be the meta positions, and these are going to be the para position. Now, if the reference group is over here, then these will be the ortho positions, these will be the meta positions, and this would be the para position here. Okay. Now, now let's talk about how to determine if a group is an EDG or EWG just by looking at it. Right. So EDG versus EWG. So this is how I think about it. You look at the first atom attached to the system, right? And the system here could be dienophile, or benzene. In this specific EAS mechanism, our system here is specifically benzene. But when we talk about Diels order, the system could either be the diene or dienophile. Because EDGs and EWGs are also used for Diels order. Okay? Now, if the first atom is negatively charged, like either partial negatively charged or full negatively charged, it is an EDG. Right? Because it has negative charges to donate. If the first atom is positively charged, like either partial positively charged or full positively charged, it's missing electrons. So it would want to withdraw electrons. So it's going to be an EWG. Now, here are the two sneaky ones that I want you guys to know conceptually. any hydrocarbon chain, like methyl, ethyl, isopropyl, tert, butyl, butyl, is going to be an EDG inductively, right? It's going to donate electrons inductively. Any halogen is going to be an EWG inductively as well, because halogens are the most electronegative atoms on the periodic table, so it's going to withdraw electrons very strongly. That's why it's going to be an EWG. Okay, so let's take a look at this right here. If we have this group attached to this, if I have this benzene system attached to this group right here, look at the very first atom attached to the benzene, which is this oxygen right here, right? We know that that oxygen is partial negatively charged because it's more electronegative than the carbon, so it's going to be partial negatively charged, and it has 2 pairs of electrons, so we can see that it can use its 2 pairs of electrons to do resonance like this. And I'm going to draw out the resonance structures out like this. Now this is more of a Levens thing. This is going to be an EDG by resonance, right? Because it's donating electrons by resonance here, as we can see. But it's going to be an EWG by induction, because oxygen is more electronegative than carbon. It's going to withdraw electrons electronegative, like inductively, right? By having a higher electronegativity. Okay, so let's draw out the resonance structures here, because this will explain why EDGs are going to direct electrophiles in certain positions. Okay. Okay. Right. Now, these are the resonance structures that will be sufficient to explain the positions here. We notice that an EDG injected the negative charge into the system, which is the benzene here. And we see that the negative charges are going to be in these positions right here. Right? This is the ortho position, this is the para position, this is the ortho position. So we see that there's negative charges on the ortho positions and the para positions. So if we have any EDG here attached to the benzene system, there will be a partial negative charge on the ortho and para positions. Right? Which will make these ortho-para positions the strongest nucleophile, right? Meta carbons here are neutral, so they're not as a strong nucleophile as the ortho and para positions. So that's why we call EDGs are ortho-para directors, right? And you can also see EDGs as activators, okay? Now, let's look at an EWG example now. So you have something like this, right? Now, you might look at the oxygens here and say that they have pairs of electrons. They're partial negatively charged, and you might say EDG right away. But we cannot say that because those oxygen atoms are not the very first atom attached to the system. Our system here is this benzene. The very first atom attached to the system is this carbon here, which has a partial positive charge. So that is going to be an EWG. This entire group here is going to be an EWG, right? It's going to withdraw electrons by resonance like this. And then we could draw another resonance structure out like this. And then another one right here. And this will be the last one that will be sufficient to explain the positions here. Okay. Now, we're not going to be concerned about the group. We're going to be concerned about the system, which is the benzene. We see that when we added an EWG onto the benzene, it injected a positive charge onto the benzene. It stole or withdraw electrons from the benzene. That's why there's positive charges on the benzene now. And if you notice about the positions of the positive charges, they're also at the ortho and para positions. So whenever you have an EWG attached to a benzene, there will be partial positive charges, ortho and para, to the EWG. Now, we said earlier that benzenes are the nucleophiles of the mechanism. The best nucleophilic atoms here will be the meta positions. There are no formal charges here, right? On the resonance structures, they're neutral, which is a better nucleophile than positive charged atoms, right? So that's why we will say EWGs are meta directors. Now there's one exception, right? And the exception here are the halogens. Right? Halogens are EWGs, but they're not meta directors, they are orthopara directors. Now here's why. Right? There's like actually multiple reasons, but Helix didn't go over that really, so I don't want to overwhelm you guys with that. Information unless you guys want to know. But know that when you see engine like chlorine or bromine, they are weak EWGs, right? Weak EWGs. So Friedel-Crafts reactions can still happen on benzenes with just halogens on them, but they will be orthopara directors, not meta directors. Okay. Okay. So now we'll talk about the helper reactions, the other reactions that we could use for mechanism here. Sulfonation, alkylation, acylation. Yeah. Right. Because like, let's say we have this benzene here. Let's say we have this group here, and we have these reagents here. Right. Would you guys say this is an EDG or EWG? You guys, 3 predicted products here. Because this is actually important as well. Actually, no. Let me give you more to explain this concept. This is an important concept. Okay. 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 Um, let me see. Let me show you the list of EDGs and EWGs here. Because there are strings to these. Right here. Okay. Let me just copy and paste this over. So then I can show you guys, so you guys can do the problem. And explain it to you as well. Let's see. Okay. Okay, this is selection. Okay. Okay. Okay, let's share screen again. Okay. So here's the reference line, hydrogen, because hydrogen is not an EDG, not an EWG. Here's the EDGs, here's the EWGs, right? The strong EDGs are here. The moderate EDG, but no, these are the strong EDGs. So let me make a line here, right? Strong, moderate, reference the hydrogen, proton, and then weak, moderate, strong, EWGs. Now, the reason why it's in this direction is because going from right to left is talking about activating power, right? Activating the benzene power, activating power. And this right here will determine what the directing group is, right? Directing group, right? What group will direct the electrophile? So if you had, let's say, a strong EDG versus a moderate EDG, a strong EDG would overpower the moderate EDG, right? So the strong EDG would be the directing group. So we would look at that as a reference group for orthopara. If you had a strong EDG versus a weak EDG, you choose the strong EDG. You ignore the weak EDG. If you had a strong EDG versus a weak, moderate, or strong EWG, then you choose the strong EDG, right? Now, if you get to the EWGs now, this is gonna get kind of confusing. A weak EWG would overpower a strong EWG, right? Because the weak EWG does not deactivate the ring as much, whereas a strong EWG deactivates the ring so much that it won't direct the group, right? So keep that in mind for the EWG. Okay. Now let's take a look at the first problem here. How would you guys approach this problem here? And then I'll look at the next reactions here. Okay. Multiple directly groups. Okay. Yeah. Okay. Okay. So, we see that this benzene here has this group, which is an EDG, because if you look at the first atom attached to the system, it is partial negatively charged with 2 pairs of electrons. And because it's an EDG, we know it's an ortho para director, right? And because there's only one group here, we don't have to worry about any other groups, any competition here to direct the electrophile. So I'm just gonna dot the ortho and para positions, where because I know I'm using HNO3, H2SO4, I'm doing nitration here, which is gonna add an NO2 group to the benzene. So we could have 2 products here. One would be major, one will be minor, right? So one product here would be if we added the NO2 group para to the EDG. The other product would be if we added the NO2 group ortho to the EDG, like that, right? Now, the para product would be major, the ortho product would be minor because of steric hindrance, right? These 2 groups are so close to each other, they're going to bump into each other, making it less stable, minor product. Whereas the para product, those 2 groups are on opposite ends of each other, avoiding steric hindrance, avoiding bumping into each other, so that would be more stable, major product. Now, if we look at the second reaction here, this NO2 here would be an EWG. It's one of the strongest EWGs actually, because if you look at the expanded Lewis structures, the first atom attached to the system, which is this nitrogen here, has a full positive charge, right? And because this right here has a full positive charge, it's an EWG, which is a meta director. And the meta positions would be here or here. There's no other groups. We don't have to worry about any steric hindrance or competition of directing groups. So we just add a bromine to one of those positions and get our final product there. Now for the next problem here, we have this halogen, which is, like we said, the exception. It is a weak EWG, right? But it's not a meta director, but it is an ortho para director. And because we're using sulfonation reactions, we're going to add a sulfonate group to the benzene, ortho or para to the chlorine, right? The major product, like we said earlier, would add the SO3H group, para, to that chlorine. And the minor product would have the SO3H ortho to that chlorine because of steric hindrance, right? This would be major. This will be minor. Okay. Now we'll get into polysubstituted or multiple substituted benzene rings, right? We have this benzene attached to this group and this group, right? If you look at the chart, this would be strong EDG. This would be a weak EDG, right? And the reason why is because this strong EDG here has 2 pairs of electrons that could use to donate electrons directly into the benzene, whereas this hydrocarbon here is just donating electrons inductively. There's no resonance going on there. So because we have 2 directing groups here available, we choose the one that has a higher activating power. Which one will activate the ring as much, right? Or if they're both EWGs, which ones will not deactivate the ring as much, right? So the strongest activator here is a strong EDG. So if I locate the ortho and para positions to this EDG right here, we have this open position and this open position. This is already taken, right? Now the major product would have the acyl group attached to the para position. To that directing group. And then the minor product would have it here, right? And it's especially minor because there are 3 groups adjacent to each other, steric hindrance, right? Yes, Ashna?
I just had like a question.
Mm-hmm.
Between oxygen and like nitrogen, if they're an EDG, like they're both having a negative charge, would nitrogen be stronger or?
Mm-hmm. Yeah.
Okay.
Nitrogen would be stronger. Correct.
Okay. Okay, thank you.
And that is because if like let's say we are comparing this versus this. They're both EDGs, but like you said, nitrogen is the stronger EDG because think about electronegativity here. Which atom is more electronegative, nitrogen or oxygen? Which one is more electronegative?
Nitrogen?
So if you look at the periodic table, nitrogen is on the left of oxygen, right?
Yeah.
Oxygen is to the right. So electronegativity increases from left to right. So oxygen is more electronegative, nitrogen is less electronegative. And because of that, oxygen wants to keep its electrons. It does not want to donate electrons as much as nitrogen does, right? Because nitrogen is less electronegative, it's more willing to donate electrons. That's why it's a stronger electron donating group, right? Nice. Okay. Now we have this right here, which this is a strong EWG. This is a weak EWG. Which group would you say is going to be the directing group? Which group would direct the electrophile? The strong EWG or the weak EWG?
The weak EWG.
Yep, the weak EWG because it does not deactivate the ring as much. So we're worried about the meta positions relative to that weak EWG, which are these positions right here. Let's say this is point A, this is point B. Where would the chlorine go to get to the major product?
Meta.
Meta, meta on carbon A or carbon B? Because both carbons A and B are meta to this aldehyde, weak EWG.
A.
Yeah, correct, right. Because there's less steric hindrance there. Chlorine. Okay. Now we see here we have a weak EDG versus a strong EWG. Which one would take priority? A weak EDG or a strong EWG?
A weak EDG.
Correct. A weak EDG. And we know EDGs, all EDGs are orthopara directors. So we're gonna locate them right there. Now this one here is gonna be especially minor if we add it here because it's gonna be in between these two groups. So we don't not want to add it there at all. But the two other products that can get formed are the two other positions that I'm gonna draw out here. Okay. Okay, nice. Uh-huh. How would I know when a weak EDG would take priority over a strong EWG? Yeah, so we know a weak EDG would take priority over strong EWG because in the mechanism, benzenes are the nucleophile here, right? And EDGs will donate electrons into the benzene, making it a stronger nucleophile, making it able to do its job better. But EWGs withdraw electrons, making the benzene weaker, deactivating the benzene. So all EDGs will always overpower all EWGs, no matter the strength, right? Because all EDGs activate the benzene, making the benzene stronger, more nucleophilic, whereas all EWGs weaken the benzene, make the benzene slower at these mechanisms, right? So that's why when we talk about EDGs, strong will always overpower moderate, which will always overpower weak. And that's more intuitive when we talk about EWGs, right? Because when we talk about EWGs, weak EWGs will overpower moderate EWGs, which will overpower strong EWGs, right? Because the weak EWGs do not deactivate and slow the benzene as much as the strong EWG, right? Which can be represented by this list right here. We talk about the directing group as the activating power. The strong EDG goes first, but then moderate EDG, then weak EDG, and then the reference group, which is the hydrogen, and then the weak EWG, and then the moderate EWG, and then the strong EWG. We see here that these three categories here are EDGs, and we see that these three categories here are EWGs, and we notice that EDGs, all EDGs, no matter the strength, will always be stronger than EWGs. So if you compare any weak EDG to any strong EWG here, the EDGs will always overpower the strong EWGs. Okay. Did that answer your question, Gabby? Yeah. Of course. I'm not sure if it was mentioned already, but is there a major and minor product for this question? Yeah, so there is definitely a minor product for this question, which is going to be the one where we added at this position where it's in between these two groups, right? So we do not want to see three groups adjacent to each other like that at all. That's very unstable. So we could either have this structure or this structure. And if we were to choose which one's major, which one's minor, which one do you think is major, which one do you think is minor based on steric hindrance? Like which one do you think, let's say, is a bigger group? Yeah, that could help you maybe figure out which one's the major minor product. The isopropyl is bigger. So the isopropyl has carbons attached to carbons attached to carbons. Whereas the NO2 has a nitrogen, double bonded to an oxygen, single bonded to an oxygen like that, right? So carbons would be smaller atoms compared to nitrogens, but by a small amount. So they would be like relatively similar in this case. But I would say NO2 would be bigger, and because of that, I would say this is the major product because we do not want the big groups next to each other, right? Yeah. So I would say the top one here would be major, and the minor one would be minor here. Yeah. Okay. Yeah. Okay. Yeah, it just looks smaller because it's condensed, but if you expand it out, you'll see that the nitrogen here is attached to oxygens like this. Nice. Okay. Now we are going to talk about one. Yeah, we already talked about that. 1, 2, 3, 4. Yeah, 4 different helper reactions here, right? So we're going to talk about how hydroxy groups and NH2 groups are reactive. So let's say we have this benzene, and we have an NH2, and then we try to do Friedel-Crafts alkylation with this haloalkane and metal Lewis acid catalyst AlCl3. We know this is a strong EDG, so you might think that we're gonna add this group onto the ortho or para positions, right? That's if these carbons here are the nucleophiles, right? But the strongest nucleophile here would be this nitrogen here with the negative charge. That is a strong nucleophile itself, which will overpower the nucleophilic carbons of the benzene right there. So because of that, we're gonna have this product instead. Where the nitrogen, right, is gonna be the nucleophile that attacks this carbon. So this is the star. This is the new bond between the star and the dot. The dot is attached to an ethyl group and a methyl group. And throughout the mechanism, right, we lose 1 proton of the nitrogen in order to maintain the neutral charge of nitrogen right there, giving us this neutral product here, right? Now think of this as a SN2 mechanism. Nitrogen attacks that carbon, kicks out the chlorine, right? Make a new bond right there, SN2. But then that nitrogen, if it has it will be positively charged. So then we could use like a chlorine minus ion that got kicked off to deprotonate it to make it neutral, right? So when you have an NH2 or OH, always look out for that, right? This is a sneaky concept right here. Okay. Now, if you have, let's say, the same thing for, let's say, OH, and you do bromination, right? We're gonna get the major products here, which is gonna add bromine to the para position. And then because this is a very strong activator, we're gonna keep going here, right? Now we're gonna add the bromine to the para position to the EDG like this. And then we could go again because there is another ortho position open up there, which will give us this here. Okay, nice. Now, we can control the reactivity of the NH2 and OH by making it weaker. Let's talk about the aniline, which is the benzene with the NH2 here. And if we use these reagents here, this acyl chloride with pyridine base, we're gonna get this amide here. Right. Now this is a 118C reaction, which you do need to know like the transformation of, but you do not need to know the mechanism of. Like you do need to recognize that this amine here reacting with this acyl halide would create this amide right here. Right. Basically, look at this acyl group of the acyl halide and connect it to the nitrogen, which is this part right here. Right. The red dot carbon, let's say, is this red dot carbon right here. Is this red dot carbon right there. Right. And this right here will be the neutral bond between the star nitrogen nucleophilic atom and dot right there. The chlorine leaves in the mechanism. Right. This is the first thing you're learning in 118C. This is now a weakened nucleophile. It's weakened because we noticed that the pair of electrons here is now able to do resonance, more resonance with the carbonyl here. And because we increase resonance, we increase stability, that makes it less reactive, right? It's more stable, so it's happy, less reactive, less nucleophilic. Now, that is going to be important because if you want to go backwards in synthesis, like let's say you get this and then you do whatever reaction you want, but you want to get back into this NH2 group, you can do that by using NaOH and heat hydrolysis reaction, right? Just know the reagent, don't worry about the mechanism yet. Right. Now the next thing here is going to be talk about phenol, which is an alcohol on a benzene. To weaken this nucleophile, we could use a 118A reaction, and you know the mechanism of this as well. This is going to be Williamson ether synthesis, where we create an ether from an alcohol, which is going to have base, which will deprotonate this alcohol to greater alkoxide, which will then do SN2 with this alkyl halide to give us this ether here. And we learned that ethers are relatively unreactive because they are stable, right? Like that. And that would make it weaker. And now to go backwards here, you could use concentrated HI acid, right? Like that. Okay. You will not get tested on the mechanisms of these here. Just know the transformations and why it is useful for synthesis. Okay. And we said earlier, Friedel-Crafts reactions do not work if the benzene is electron poor. Okay. So let's say for synthesis, we have this benzene and we want to create this product here. We see that we have an NO2 group and an acyl group. So we know that the two reactions that can do this are nitration and acylation, right? There's going to be two routes that you can think of, right? Let's say one route you think of is that we do nitration first with HNO3, H2SO4, which would add a nitro group anywhere. It doesn't matter here because there's no directing groups. Now, we know that this NO2 right here is an EWG deactivator. So when you try to do Friedel-Crafts acylation to get into that final product right there with the acid workup, this reaction would not work. There would be no reaction here because this right here is a deactivated ring, and NO2 is a strong deactivator, strong EWG, so Friedel-Crafts reactions would not happen here, right? And this would happen because NO2 EWG meta director, this is meta, it works out, but like this is a deactivated ring, that's why there would be no reaction there. So you gotta do another route. You gotta do Friedel-Crafts acylation first. Second step, acid workup. That's why the order of these reactions matter here in synthesis. And then we could see that with a lot of practice, right? This is one example of it right here, where when we do Friedel-Crafts acylation, right, we could add it anywhere, doesn't matter. We know this is an EWG meta director, which we can do nitration with HNO3, H2SO4 to add the nitrate group on the meta position relative to this EWG. Right, so this would be the correct route, right? We use the same reactions, nitration and acylation, but we did it in different order. That's why the order of the reactions in the synthesis here really matters. Right, okay. Now, we're gonna talk about this where we can change the directing group preference. If we have an alkyl group like this, we know that this right here is an EDG, which is an orthopara director, right? You can think of it as an activator as well, right? If you want to make it into an EWG, you can do that by using Jones, CrO3, H2SO4, H2O, which will oxidize the benzylic carbon, the carbon attached to the benzene, to have a carbonyl, an acyl group. Like that. Don't need to know the mechanism, just know the effect that it has, the transformation that it does. Right? And we know that this right here is an EWG, which is a meta director, a deactivator. Now this is important for synthesis, important tool for synthesis. Right? This isn't an EAS mechanism. Right? It doesn't follow the EAS steps. But this right here will transform this EDG into this EWG, will transform this orthopara director into this meta director. Now, you could go the other way. Like if you had this meta director to start off with, and you want to go to an orthopara director, you could do that by reducing it with H2PDC, reducing agent, or some metal like zinc and hydrochloric acid, HCl. Don't need to know the mechanism, just know the transformation and reagents that will convert this EWG into this EDG, meta director into orthopara director. Okay, now if you have aniline, NH2, which is an EDG, and you want to make it into an EWG, NO2, right? Strong EDG to strong EWG, you could use a peroxy acid like this right here. And then if you want to go backwards from EWG to EDG, you could use reducing agent H2PDC or a metal with HCl. And the metal could be like zinc, Clemmensen reduction. Okay. This is good for synthesis here, not EAS, but good to know for synthesis, right? Okay. Because we know that this is activator, EDG, orthopara director. Now we know this is a deactivator, EWG, and because it's not a halogen, not an exception, it is a meta director. And we could go back and forth there for synthesis. Okay. Now the last thing here for synthesis is protecting the ortho position. Because let's say, for example, we have this toluene, which is a benzene with a methyl, and we want to get this in 100% yield. Right? If we do nitration, we will get this, but we won't get this in 100% yield because we know that this methyl group, OR group, is an activator, EDG, therefore orthopara director. And the orthopara positions to this group are these purple positions here. So we see that this will get formed because this NO2 is ortho to that. But this will not get 100% yield. right? Because this is actually the minor product if we just do it like that. The major product would be if we added the nitro group para to that EDG, right? That will also get formed. So let's cross this out and block the para position so the nitrate group cannot go there. To do that, we're going to use sulfonation, SO3, H2SO4. And because the thing that gets added is so big and bulky, SO3H, we're going to exclusively add it para to that EDG right there to block the para position, right? That this is the purpose of this step, block para position. Now, once that's blocked, we now can do nitration, right? But we now have two groups. We have this group and we have this group. This is a weak EDG. This is a strong EWG. And like we said earlier, EDGs will always overpower EWGs because they activate the ring, activate the benzene more, the nucleophile more. So it's going to be an orthopara director relative to that methyl group. NO2. The para position is already taken, so we don't have to worry about that, right? It's blocked. Now to unblock the para position, we could do desulfonation with dilute H2SO4 and water. Right, now this is for synthesis, right? Now this is when we deblock para position. We unblock the para position. Okay. Any questions on this? Okay. Okay, that's good. Sunday, March 1st, 3 to 5 p.m., I will have an extra midterm review session just to go over practice. But this review session will be up on YouTube, so you guys can review that whenever you guys can. Okay. I hope that helps, and good luck on the midterm next week, guys. Have a nice day.
Thanks, Brian.
Of course. Bye bye.